Okay. All right, guys. While we are waiting for the computer to work, so I can just start the lecture from my tablet. Um, so last time, the last thing we talked about was the instructions to the architecture, and then I told you that this is the interface between the hardware and software, and it allows the hardware and software to basically develop independently, right? And the majority of the lecture today is going to be actually about that. And then I also told you about what software and hardware understands from each other. So the software basically understands the functional description of the hardware. This includes the storage locations, which is different type of memory or variables, as well as the operations like add and multiply and subtract and so on and so forth. Hardware basically what it understands is much simpler version of the system, which is an instruction sequence of instruction, their order, and what they do. Okay.
We need to replace so after class.
Okay. All right. So as I said, our focus in this class is RISC-V architecture, and I'm going to talk about why this is important and this is useful. So before actually jumping into the ISA, which is kind of the focus of this week, I want to also give you a little bit of a background on the main things that we care about historically about computer architecture, and kind of give you a quick overview of the topics that we're going to go over, which is kind of from historical perspective. That's kind of also how we develop, fast computers. So I have this question for you: what is the main objective of architecting a computer? So now let's say that you are a computer architect and you're starting a new company. What do you think would be the main objective when you want to design a new CPU? Speed, yeah. So performance is that's the number one. So it's usually what is driving the innovation in computer architecture is performance. You just want faster and faster systems. Beyond performance, there are other things. Cost. So you want to have kind of different tiers of the system, and maybe some lower tier and higher tier. Reliability is also kind of it's another thing that you want to guess. Yeah. Power efficiency is another very important. So it's usually after performance, the second important things in any design is the power efficiency. But although, as I said, what you will see is that you want systems to be fast first. So you care less about power efficiency or the cost if it's a high-end processor. But once it goes down to a lower tier processors, then you start thinking about these other things. Yeah, accuracy is true, but accuracy is sort of given. So you want your system to work, right? So it's kind of reliability is within the same ballpark, right? So you want your system to be correct most of the time at least, right? So to kind of like answer this question in a nutshell, you want computers that are efficient, and now you can ask what is an efficient computer, and as I said, the most obvious answer is an efficient computer is a computer that is fast enough, right? So performance is kind of the king in computer architecture. You want systems that are fast, and then the latest and greatest generation of any system, talking about NVIDIA, Intel, Apple, and so on. The first slide that they show in the presentation is that, okay, this generation is faster than the previous generation by this much. That's the very first thing that they show you. And it's always like that. It's always going to be like that, okay? But then in addition to that, as I said, depending on the computer type that we are thinking about, then power efficiency also becomes an important issue. Think about, for example, your iPhone. Your iPhone needs to be fast, but also needs to have a decent amount of battery that it lasts, for a day or more than a day. And how do you get that? So you get that with having bigger batteries and better batteries. But more important than that is you get that by having power efficient designs, okay? In this class, we're not going to talk much about power efficiency. We're going to mainly focus on the features that help us to get better performance. But just keep in mind that there is a whole bunch of things that is also done on the power efficiency side as well. And then as someone says, cost is, for example, is another important thing. usually this cost is translated into area. So how big your chip is usually the deciding factor for the cost of it, what technology is being used in your system. So these are the important things when you're thinking about your system, okay? And then of course reliability and security are other kind of secondary order problems. Unfortunately, as recent development has shown, is that not considering security specifically as a first order issue has created a lot of problems, and that's particularly what I'm basically doing research on. I'm going to actually give you a little bit of that of like a security flavor later on in the course after kind of week 5, week 6. So you're going to see a little bit of the issues well in a system. So as I said, kind of like the summary is that performance is typically the most important component in any system. Okay. So as I said, I want to give you kind of like a quick kind of history of computers and how we actually get to this point, and to kind of help you understand why we make those different decisions, and then we're going to start talking about them one by one. Okay. Actually, if you think about like computer architecture and generally computer systems, is that if you go back to few decades ago, which is not actually very far, we came a long way. So the picture I'm showing on the left is a computer called ENIAC, which was used during the World War II. And the computation power of this entire room is significantly less than what you get now on your smartwatch. Okay, so think about just the amount of power and energy and area that it was occupying versus what we do have now on your wrist is actually quite amazing of how things has been changed. This picture is the one that we're going to actually talk about for a few minutes. This is actually showing you kind of 5 different eras of computer architecture, and it starts with basically this initial point to picture, design point, which is this the picture that I showed you in the previous slide, which is kind of like the first kind of workstation computer that we started in 1970s. So if you actually normalize the performance of the system that we get from that computer all the way to the system that we have nowadays, and this picture is not the most up-to-date, this is from the book, which was published in 2018. The interesting thing is that, so this is, at that time, this was the latest and greatest Intel Core i7. The interesting thing is that if you look at the number, you will see that the performance has been almost 50,000 times faster than what we have in 1978. Okay, so from 78 to 2018, which is not very, very long time, we actually managed to make a system that is 50,000 times faster. And this story is kind of continuous. Another interesting thing that you can see is that this growth it has different pace. So for about 10 years, we have around 25% per year improvement. Then during kind of like, late 80s to early 2000, we had about 50% improvement per year. And this is quote unquote time that we call the golden age of computer architecture. This is when we actually come up with all these neat techniques such as pipelining and branch prediction and out of order execution and caching. So most of those ideas actually happened during this time. And then at 2004, we actually hit what we call hitting the power wall, which I'm going to talk about, which unfortunately caused the system to now doesn't go faster than we wanted to. So it's kind of like we ran out of the ideas for the core macro architecture. But then we start doing some other tricks and we managed to continue kind of like, making progress. But as you can see, kind of the speed of the CPU. So this is just the CPU. It's not the end-to-end system. It's just the CPU. As you can see, the speed of the CPU is kind of flat at the moment. So we're not like significantly designing fundamentally new computers that are order of magnitudes faster than previous versions. We're kind of like, kind of keeping the status quo. But we are making the innovations in the other side of things, including GPUs and accelerators and so on and so forth, which I'm going to talk about as well. And another interesting figure that I want to share with you is the clock speed and the power consumption. So as you can see, the clock speed, which is kind of a good filter or approximation of how fast each transistor works, is starting from somewhere around 12 megahertz. Again, in late 80s, in early 80s, in the first version of the Intel 80 8266 processors, all the way to the recent kind of latest generations of Intel processor. And again, this picture is not the most updated picture. As you can see, starting from like 12 megahertz, we are now in the gigahertz range, right? Like 3.4, 4.4, things like that. So you actually we see a significant rise in the clock speed of the system. Another interesting thing is looking at the power. So the story of power is somewhat strange. So we kind of like start flat and then suddenly rise. This was an important point in history where we actually create a lot of power that at some point the chip becomes so hot that we couldn't really go further than that. At that point, this is actually early 2000. The amount of heat that we generated on a piece of silicon was equivalent of a rocket nozzle. Like the bottom of a rocket nozzle was as hot as a CPU at 100% utilization. So you can imagine how bad that was. And at that point, unfortunately we couldn't go faster, so we start thinking about other techniques that we're going to talk about. Question? Normalized to the volume of the computers. What do you mean? Oh, so the question is that this figure and that figure, are they normalized? So the top figure are normalized based on the performance of the CPU, the AX CPU. So let's say, for example, I run a multiplication and it takes X amount of time. I do the same thing on the newer CPU and then see how much time it takes. I divide these two and that's how fast it is. So when I say, for example, it's 50,000 times faster, it means that for the same amount of operation, it's done in 50 times faster. Okay, that's how we normalize. This one is not normalized though. These are absolute numbers, right? So this one is, for example, the clock rate was 12.5 megahertz, and now it's 3,400 megahertz or 3.4 gigahertz. Okay. So as you can see again, so to kind of give you some numbers, we managed to make the clocks significantly faster, about 300 times faster. And then this figure is actually showing you the innovations on the memory side. So this is actually the biggest memory that we use in our most advanced computer nodes in each year. So starting from like, again, late 70, early 80, our computers had around 16K or 64K. There's actually this very famous quote from Bill Gates that the computer that they had, the MS-DOS, has 64 kilobytes of memory, and he said that I cannot imagine that people possibly use more memory than this. So at that point, 64K was like a massive amount of memory that nobody was imagining that you would need more than that. But if you think about 64K, it's like the picture that you're taking is now more than that, right? So it's nothing compared to that. But nowadays, of course, we are in the gigabytes and terabytes range of memory. This is DRAM, so it's not your SSD. This is just your DRAM. Another very interesting thing from this figure that is always make me think about this is that if you think about kind of this point where we jump from 1 gigabytes to 2 gigabytes, you see that it's kind of roughly takes 2 years. So in 2 years, we managed to double the amount of memory that we managed to build for the entire history. So for the beginning of the memory kind of design technology, we spent many years to manage to get to that point. But within 2 years, we managed to double that. So it kind of shows you kind of the exponential growth that we have in our systems. And again, if you look at this, we see that this is 2 to the power of 17 times more memory within this time frame, which is also a crazy number. So long story short, if I look into kind of different generations and looking at the size and the power and performance and memory and price, you will see that it's actually the numbers are massive. Okay, so like the adjusted price performance or the performance, as you can see, these numbers are massive. And again, this is not like million years of innovation. This is only 40 years of innovation, 50 years of innovation. Okay, and very very interesting thing is not only we managed to make faster computers, but also we managed to make them cheaper. And that's actually why the microarchitecture business is so lucrative and there's tons and tons of people working on it. Is that it's not I'm building something very, very fancy that nobody can buy. I'm actually building something very, very fancy that everybody can buy. And as you can see, for example, from one generation of iPhone to the next generation of iPhone, the iPhone gets better, but the price stays the same. And the reason for this is that at the microelectronic side, we managed to keep the price at the same amount. So for the same amount of money, we actually managed to build better computers, and that's big. That's excuse me. That's a very very important aspect of the system. And lastly, the size of the system is also shrinking. So again, not only we managed to make things more power efficient, more cost efficient, more performance efficient, but we make them smaller and smaller. And that's also another very, very important aspect of the system. So where are these improvements are coming from? So how do we actually manage to do this? There are two reasons. There is the innovation in the technology. This is like managing to build smaller and smaller transistors using better integration technologies, different techniques to build transistors and packaging and so on and so forth. And then the architectural technique, macro architectural techniques that we use in order to build the systems. Okay. The first one I'm not going to go through, like the transistor technology. That's a separate course for this. That if you're interested, you're going to take it. But generally, just showing you kind of like the evolution of the integration technology that we use. That early on we started with what we call vacuum tube in early 50s. But then what we are doing these days is billions and billions of transistors, right? So that was the number one reason that we managed to make these systems very, very efficient. And then this is actually, there's a very famous law called Moore's law that basically says that every 2 years we can double the number of transistors. And this was a prediction at that time. But interestingly, if you actually look at the actual product that's being built over the years, you see that it actually very nicely follows this twice 2x in 2 years kind of prediction. So yes, sometimes we were ahead of the curve and sometimes we were behind the curve. But if you try to fit a line, you actually can see that this is following. But of course, the important things about Moore's law is that this is kind of like becoming like this. So it's no longer we can actually go into that double linking. Although again, depending on who are you asking, someone says that no, it's actually going this way. So Intel, for example, is still pretty certain about that the Moore's law is still alive and doing well. There's this very famous talk from their CEO a few years back that he had this talk about like Moore's law is alive and thriving. But generally, kind of like it's definitely slowing down. Whether or not we can manage to build more and more transistors and double the number of transistors is something for many people to work on and figure out. But it's definitely less than 2x at the moment. Okay. And then the interesting thing about the Moore's law is that beyond the fact that it's actually improving the performance, it's also the law of economy. Basically, what it says is since the cost of the entire thing stays the same, now that I'm doubling the number of transistors, it means that the cost per transistor is decreasing. In other words, the reason that the new chip has the same price as the previous generation of the chip is that we managed to build more transistors with the lower cost. And that was the kind of the driving factor for Moore's law. And the reason that the Moore's law is slowing down is that no longer this sentence is true. It's actually from let's say 3 nanometers to 1 nanometer, or from 5 nanometer to 3 nanometer technology, the fab cost is massive these days that it no longer it means this. So it means that actually the overhead that you're paying from going to a lower technology is so huge. Was there a question somewhere there? Okay. So as I said, the first reason that these improvements are coming from is from the transistor and technology perspective. I'm not going to go through the details of that anymore. But what we are going to talk about, and then again, so this actually this first kind of era was massively influenced by that. But then what we're going to talk about is this architectural and computer organization ideas that we came up with that allows that not this 25%, which was coming from the technology, but we managed to double that. So this twice increasing rates of improvement of the system is because of these advanced techniques that you're using. Actually, it's been shown that if we didn't use microarchitecture the way that we did, using pipelining and caching and techniques like that, then computers today would have been 25 times slower than what we have now. So kind of the impact of the techniques that we're going to learn in this course is basically where you see that. So just by making more transistors, not going to necessarily give you faster systems. Okay? All right, so this is kind of was the trend, and then this was going all right until we reached to this point. And as I said, this was a very important point in the computer architecture history, and that's what we call a power wall. So power wall was that, okay, we were kind of adding more transistors and adding more features and be getting more and more from our CPUs. But then think about it, that you can only pack so much transistors in one silicon, because adding more transistors means that you're generating more switching, you need to funnel more power to it. At some point, you're reaching some physical limit. And that was the limit that we reached to one of the particular generation of the Intel processors, where, as I told you, that the amount of heat that we generated no longer was able, the no cooling system that we had at the moment was capable enough to make the system operating. So we are actually reaching to the dangerous temperatures that no longer the transistors were able to function properly. Okay? So the reason for this was why the amount of temperature was rising, or the amount of power leakage was rising. The reason for this is that the transistors become smaller and smaller, and become so smaller that at some point the amount of what we call a static power leakage becomes so large. If you think about the amount of power consumption that we have, there are two classes of power leakage usually we have. There's a static power consumption and there's a dynamic power consumption. Dynamic power consumption is that when your transistors are switching. Okay, so when your transistors are switching, you move the current from top to bottom or bottom to top, whatever, and then you're charging some capacitor or discharging some capacitor. So that requires some energy. But then when your transistor is off, you can think about this as an ideal switch, which means that it's no longer actually consuming any power. That's the assumption that we have in any system, that when it's off, then it's not consuming any power. In reality, is that it consumes just a little bit of power. The reason for this is, I mean, again, I'm not going to go through like the physics of the transistors, but think about this kind of like, this two channels that we have in the transistor, source and drain. If these two guys become so close to each other, then there is actually opportunities for these electrons to tunnel. Okay, and when they tunnel, you actually leak power. So even if there is no channel and there's this transistor is supposed to be quote unquote off, since they are very close to each other, there might be actually a small amount of leakage. It goes through lots of physics and device physics that we're not going to talk about, but just know that once these devices get closer and closer to each other, unfortunately, there's the opportunity for leakage. Okay, so at that point in history is actually when the transistors become very small, that this static power leakage has become so significant. And since you had billions and billions of this, think about all of them were supposed to be off, they're actually leaking this amount. So this actually caused lots of problems in terms of power consumption, and we had that problem. Okay. So at that point, we no longer can, although we had the technology to increase the number of transistors, but we couldn't increase the number of transistors because we couldn't power them on. Okay, so what we did instead, and this is, by the way, called the phenomenon called hitting the power wall. So what did we do instead? we come up with the idea of multi-core systems. Okay, so at that point, all the systems were single core. So we had like a very massive, Pentium 4 or Pentium 3 or whatever. But then we realized that okay, one core we can no longer make it bigger. So what is better than one core? Multiple cores, right? And if I can somehow kind of like abstract the multi-coreness of the system away from you, you have this illusion that I have a massive core with multiple cores at the same time. Okay, so the multi-core was kind of like the trick that allows the system to scale further. And the thing that you can do is that then you can power each of these cores separately, right? So I can have a power here and a power here. Then I can have like a good heat sink here and a good heat sink here. So I kind of distribute this kind of power management and thermal management of the system, so I still can increase. So if I think about the total number of transistors on the CPU, I technically increasing it by increasing the number of cores, but the reality is that each core kind of stays the same. Okay, so that was kind of like the key technology, and then the ultimate version of the multi-core is GPU. So GPU is a system with this very, very massive amount of parallel cores. So each core is very tiny, but I have thousands of these cores, small tiny cores together working in synchronization, allowing me to do a lot of parallelization. Okay, so we're going to actually talk a little bit about this multi-core, the problems that we face with multi-core, how we fix them, and so on and so forth. Okay. So starting 2005, basically we are in the multi-core era, and we technically still are in the multi-core era. And here we actually come up with what we call a thread level, task level, and program level parallelism. So think about CUDA, for example. For those of you, how many of you knows how to write a CUDA program? A few. So the way that you write a CUDA program is actually you're parallelizing, you're kind of dividing the work into multiple systems and so on and so forth. So that way you can actually extract more performance out of your system. Okay, so this is basically was this era. Okay, then it comes around 2011, 2012, and that's when we kind of like also again slows down. The reason that we slowed down at this point was there was limited amount of parallelism that you can extract from the system. It's not like if I double the number of cores, my system gets 2 times faster. Why? Because of this law called Amdahl's law, which is basically say that if I have n number of cores or p number of cores, okay, the amount of speed ups that I'm going to get, sorry, if I have s number of cores, the amount of speed ups that I'm going to get, the part that can be parallelized gonna be shrink by that factor. So for example, if I have 10 cores versus 100 cores, the 100 cores give me 10 times faster on the parallelism part. But unfortunately, there's also the part that cannot be parallelized. Okay, so for a program, think about this: that I need to read inputs. I need to also write it from, read it from a file and write it to a file, and then I can multiply the numbers. The multiplication can be parallelized, and I can, feed more and more cores to the system to make that thing parallelized. But the reading from the memory part, if I have only one port from the memory, I cannot parallelize that. Okay. So eventually, if I make the multiplication extremely fast, I'm going to be bottlenecked by the part that I cannot parallelize. Okay, and that's basically program dependent. Okay, so for example, if I tell you that I have a program that 80% of it is parallelizable, but 20% of it is not parallelizable, then you can basically see what is the limits of this system. Like how fast, if I have all the cores in the board, how fast this system can get, right? So you can actually plug in numbers or for example, for a system with only one core versus with a system with 2 cores, so this part gets 40, but this part stays 20 if I have 2 cores, right? So you can actually plug in different numbers and kind of think about this. Well, what happened during this time was most of these benchmarks and workloads that we were working with was generally kind of like it was at their limit. So it doesn't matter how many cores I'm adding to the system. That's why if you actually look into high-end servers, typically they have 32 cores or 64 cores. You rarely see that these systems goes beyond that because there's not much at the CPU level that you want parallels. Okay? And this is basically kind of like where we are. And then, of course, another problem that we face is what we call dark silicon. Dark silicon is that I told you that yes, you can actually kind of separate these cores and then power them separately. But at some point, again, you need to power the cores in a very confined area. So what happened was that people actually showed that at some point you cannot really add more cores because you literally don't have enough power to power them on. So you will have this what we call dark silicon, which is part of your silicon is not being powered and it's dark. Okay, so there was actually a very interesting article that shows that, for example, a system with many cores, what will happen is that you probably can power this one and power this one and power this one and maybe power a portion of this, but this entire thing here will be basically not powered on, will be dark, which means that if I even add more cores, there's not going to be any benefit because I cannot power it on. So that was another problem that we face, which is known as dark silicon problem. Okay, and this is kind of like where we are at. So we are kind of like we cannot really parallelize things any further, and then we cannot really add any more transistors and or cores because we don't really have the power capability to do that. Yes. Yes, the question is that when we hit the rocket nozzle temperature, what's the power wall? Yes. So what we did next? So I mean, one thing that you realize is that always with technology, especially microelectronic technology, there was like one issue after another issue, and there was always innovation that kind of move us to the next era. And then the next era here was basically the AI. So the AI gave us this massive new opportunity to do things. So I told you that the amount of parallelism was limited by the Amdahl's law, and then there was a part that I need to read and write and all that. So here's your new workload. A massive billion parameters, trillion parameters large language model. That the problem is that I need to multiply each element to each other. So I need more cores and more cores and more cores because essentially the bottleneck is that how fast I can multiply these things. And that's why now GPUs are so powerful and so popular because they give you that capability to do these things. Okay, and then basically this is also gave us this kind of like change in the way that we are thinking about computer architecture, which used to be just general purpose, which was kind of like gave you ease of programmability and flexibility, but unfortunately it didn't give you the performance per watt that you want. But then you can go actually to massively customize designs like TPUs or accelerators that it doesn't give you programmability at all or the flexibility. It's actually hardcore kind of functional, let's say matrix multiplication, but it gives you a massive improvement in the performance per watt. Okay, so we are kind of now in this era that we need all of them. So we need GPUs, we need CPUs, and we need accelerators, but the majority of innovation is basically happening on the customization because we kind of saturated things that we could do on the CPU side. Okay. So it's kind of the takeaways from this kind of historical lecture is that we actually managed to do a lot of great things and innovations in order to make the computers faster. So we kind of like sustained the 2x per 24 months Moore's law prediction, and we kind of continuing to some extent doing that with various different tricks, such as adding the adding the multi-core and kind of adding other customization, but we still managed to make the computers faster. Macro-architecture tricks and innovations and features, the majority of this course is basically was responsible for 25x improvement in the performance. And then we hit various different problems, including the power wall and the dark silicon, but we managed to actually go beyond that. And then we introduced multi-core and GPUs and customizations to do that. important thing is that the reason that we need further improvement and we need people with various different understanding is that now we are at the point that no longer you can just pack more transistors and be happy with what you get. You actually need to understand the workload first and then go down and actually optimize your system. That's why we need customization. And in order to be able to do customizations, you need the cross-stack understanding. You need to understand the operating system. You need to understand the workload. You need to understand the AI to be able to contribute to the hardware, and vice versa. If you are at the AI level, you need to understand the lower level. So that's also a motivation for why we need, as a computer scientist or engineer or electrical engineers, why we need to understand these things. Okay, so that's kind of the end of the kind of the introduction part that I wanted to talk about. Any questions? Okay, so then we can go to the next slide. All right. So with that, I want to talk about the second important concept that we're gonna maybe talk about this week, this lecture, and rest of this lecture and the next lecture. Hopefully, we can finish it. Which is the story of ISA. Before that, few logistics. So PTEs for master students, I think most people are in. But if you are an MSc student or PhD students wants to get in, during the break, just come to me and I'll give you. Yes. I put it on the website. Just refresh your browser. It's usually cached, so you just either use an incognito or using a separate browser, and you'll find. Yes. Yeah, I mean, unfortunately, I'm using my tablet today, so I cannot like hyperlink it using the Excel sheet. Is there any? Can someone copy it and post it on CampusWire so people can actually, whoever can actually copy it, please copy it on CampusWire so people can use it. I can give you. Let's have a 5-minute break as well so that people can actually load this. You. All right. Those of you interested in honors class, please come to the class on Thursday. I'm going to talk about how to enroll. We're going to have limited, so we may not be able to accommodate everyone, but we're going to talk about it. So honors section class, question related, just come to the lecture on Thursday after the class. The lecture is at 2 p.m. right after the class in Bolter Hall. I don't remember the class number. Okay. The third important thing, and this is applying to everyone, is so this week, since we still haven't the homework out, there won't be a regular discussion session. So no discussion session on Wednesday and Friday, but the TA will be there on Thursday to give a live lecture. So if you are interested to listen to that, go to the Thursday discussion session. It doesn't matter whether you're enrolled. Generally, it doesn't matter which discussion session you're enrolled. You can go to anyone you want. Okay. But if you want to watch, get the lecture from the TA, go to the class. But the lecture will be also recorded, so it doesn't matter if you cannot attend. There's no attendance will be taken or anything else. So it's just informational. If you want, go and watch it live, or the video will be posted immediately after the lecture. Okay? Starting next week, we're gonna have our regular discussion sections. Okay? Any questions about discussion sections? Starting next week. Yes. Yeah. No, the TA's discussion does not count for participation. Thursdays does not count toward your participation. In general. Not this week, not other weeks. You have to go to Wednesday or Friday one if you want to get participation. But you can go to anyone. Any other question? Yes. It's various. It's a start from 12 all the way to 6. There's a bunch of them, so you can just go to anyone. Just list the lectures. There's a whole bunch of discussion. Like there's like 8 discussion sections. Yeah. Every Thursday 4 to 6, the TA will be there and give you a live lecture. It's optional. You don't need to go. Okay. Any other question? Okay. All right, so let's talk about ISA. So as I told you last time, the ISA is this contract between the software and hardware. Uh, Typically designed such that it gives all the program visible states, as I told you, the registers and the memory, plus the semantics of the instruction that is operating on that state. So what type of instruction this is and how do we understand each instruction. I'm going to break down all the instructions for the RISC-V in this lecture. IBM was basically the first line of machines that introduced the idea of the ISA, and then basically decouples ISA from the microarchitecture. So microarchitecture is implementation of the ISA. One implementation might be very different than the other implementation. So for example, if you buy various versions of an ARM ISA, their internals might be very, very different. As long as they can run the same set of instructions, they ISA. So for example, if you buy a chip from Qualcomm versus you buy a chip from Apple, both of them are using ARM ISA, but their internals are vastly different. Okay? This lecture will be mainly focused on the ISA itself and the interface. On the next lecture, we're going to actually talk about one instance of the microarchitecture that we're going to focus in this class. Okay? So generally, as I said, there are many possible implementations of a given ISA. For example, both AMD and Intel uses what we call an x86, which is originally was AMD 64 ISA. Okay, cell phones use ARM ISA. So as I said, Apple, Qualcomm, Samsung, Huawei, etc., they all using same implementation of the ARM ISA. Even within the same company, there might be multiple implementations. Okay. As I told you multiple times, we're gonna use what we call a RISC-V. So read it this way: RISC-V. Don't say it RISC-V. RISC-V is a standard ISA that we're gonna use it. If you're interested to learn more about RISC-V, this is an open source consortium. You can actually read more about it there. You're gonna see a lot of things there. All right. So when we want to design an ISA, we have to think about different strategies that exist. Okay. There are different actually micro-architectural style that one can take a given ISA and implement it. The most famous one is RISC and CISC. RISC is called what we call a reduced instruction set architecture. It's a hardwired and pipeline system. We actually, once we start talking about the microarchitecture, you understand what do we mean by the hardwired and what do we mean by pipeline. But the other alternatives is that you can have a microcode design, you can have a software interpretation like a Java virtual machines. But what we're going to focus on in this course is a hardwired pipeline machine. We won't have, unfortunately, time to go over the other alternatives, but just know that the other alternatives also exist. Okay? And then you can also mix and match. So, for example, it doesn't necessarily you need for RISC, you don't necessarily need a hardwired design. Sometimes you also can have micro-coded with RISC as well. And again, these things makes more sense as we're gonna move forward and actually explain the design. Just keep in mind that we are focusing on hardwired pipeline designs. Okay. So what is RISC-V exactly and why we are focusing on it? RISC-V is basically a RISC-based ISA. RISC is a reduced instruction set architecture. Reduced means that it's simple, so everything has the same size. Every operation has just one operation, and so on and so forth. We're going to actually have a separate slide comparing RISC and CISC. RISC actually developed by UC Berkeley in early 2010. The reason that it's called RISC-V was that they actually had RISC-1 and RISC-2 and RISC-3 and so on. So RISC-V was kind of like the first version of that became so popular and used. So that's why it's called RISC-V. Interesting thing about RISC-V and why it's mostly for educational purposes we focus on RISC-V is it's called open source ISA or royalty free. What does that mean is that you can basically take the RISC-V ISA, create a microarchitecture and tape out that chip and start commercially using that chip, and you don't need to pay anyone anything, okay? Versus if you want to, for example, use the ARM ISA and use the ARM toolchain, you have to actually pay the license to ARM as a company. So it's like buying a piece of software or buying some form of a royalty from the company. Okay, so for designing, usually many people are generally interested in RISC-V. There's a whole bunch of also a speculation that RISC-V will be adopted by some of the major companies, including NVIDIA and Qualcomm. And in that case, there might be then a major competition between ARM and RISC-V. At the moment, from the commercial sector, ARM still has the majority of the mobile domain computation, including all the Apple and Qualcomm and Huawei and so on and so forth. But there are commercial products that are using RISC-V as well. So just keep that in mind. It's also very nicely maintained by the open source community, and it's a majority of classes in the computer architecture using that, hence why we are using it as well. So there are multiple versions of RISC-V, so this is actually a modular design. What we're going to focus on is the 32-bit version. So there is a 16-bit version, there is a 32-bit version, there's a 64-bit version, and the difference between them is how long each instruction is. We're going to focus on the 32 version. So as you can see, it's that like the numbers is RV32, so this RISC-V 32, okay? And then there is a collection of instructions, okay? So for example, think about like, I have an add instruction and a multiply instruction and load instruction and so on and so forth. One way of designing an ISA is that combining all of them together and have support for all of them. Another way that RISC-V based approach basically following is taking a modular. So basically saying that, okay, what is the minimum set of instructions that I need to basically do simple operations? And they call that the base version, or B, okay? Then they have these additional things. So for example, if I want to support multiplication or division, or if I want to support floating point operation, if I want to support privilege and operating system-based actions and so on, I add more things. So basically what you will see if you go through the documentation of RISC-V, you will see that it's like you have things like RV32, I, and G, and M, and so on and so forth. What we're going to focus in this class for educational purposes is just the base model, which has the core functionalities. The others follow the same format. If you're interested, you can always look into the documentation. Okay? All right, moving on. As I said, RISC is basically stands for Reduced Instructions in Computers. Yes, question. So question is that when I said macro-architectural style, did I mean chip design? No, macro-architectural style is that, okay, if I give you, for example, I want an add instruction that takes 3 registers, that basically what it does is R3 is equal to R2 plus R1. How do I implement this in hardware? Like what is how do I read the variable? Where do I store it? Where do I add them? Stuff like that, okay? This is what we call the macro architecture. It's actually different blocks that you add them together and so on and so forth. This is actually a good portion of next week's lecture going to be about the macro architecture. So by macro architecture, we mean that. There is a lower level than the macro architecture, which is the hardware design that is, okay, I need to design an adder. How do I even design an adder? And that's kind of the lower level than that. So you're staying at the RTL level. Okay. So alternative to RISC is complex instruction set computers called CISC. The difference is RISC is fixed size. As I said, for example, 32 version of RISC-V is all the instructions are always 32-bit, versus CISC is actually changing. So one instruction might be 16-bit, another instruction might be 32-bit, another instruction might be 64-bit. So it's actually decoding instructions is more complex in CISC-based architectures. In RISC-based architectures, operations are simple. So you either do adding or multiplying or subtracting or XORing. You do one at a time. CISC sometimes is packed operation, which means that you might do add and multiply in one instruction. So you write one instruction that might does multiple things at the same time. And then usually that means that generally the complexity of CISC-based architectures are significantly higher than RISC-based architectures. But there's a whole bunch of opportunities to combine them and mix them and make them more interesting. The most important kind of like a CISC-based architecture is, as I said, x86. So all the interprocessors are based on CISC-based, but almost every other major company and product is a RISC-based, and generally RISC-based is significantly more favored because of the simplicity that it brings. The reason that Intel is really not switching is that they have tens and 10 years of tool chain and support. So it's like a switching from quarter system to a semester systems. Everybody knows semester system is the better option, but switching to a semester system require a lot of efforts that nobody wants to pay that, right? So similar idea. Quarter system is CISC, semester system is RISC. So think about it this way. If you are more interested about RISC versus CISC, there's a nice article that you can actually click on it and look at it. It's kind of give you a little bit more in-depth comparison as well, if you're interested. Examples of famous and popular RISC-based ISAs is MIPS, ARM, including all the M series, Apple's PowerPC from IBM, and of course RISC-V. All right. So now that we understand kind of the basics, let's actually go through the details. So how do we actually run instructions on a computer? Majority of the computers, especially the CPUs that we are focusing on, using this thing called stored program computers, or von Neumann model. So what is a von Neumann model? Von Neumann model is basically saying that I have sequence of operations which I call an instruction. I go through them one by one. I execute them. I store the results. I go to the next instruction, run them, store the results, and go to the next one and next one. Okay, that's why we call this a stored program computer. Okay, so basically I go through this one by one until I finish the end of the program, and then I go to the next program and next program if there is any more things to do. Okay, so essentially, if you think about this system, I have one what we call a linear memory, which all the data and program are basically stored in the same place. So I can basically modify instructions and data as I wish. So there's no significant difference in the way that I store instructions and data. I can maybe section the program into different sections, like code section and data section and instruction section and so on, and store them there. But typically, they just store them as zeros and ones in the memory. Then I have this thing called program counter. The program counter is basically a pointer that points to the current instruction that's being executed. So I always have a dedicated register or variable in my CPU that basically points that this is the current instruction that's being executed in the system. So if I want to execute an instruction, I change the program counter to point to that instruction and I execute it. If I want to go to the next instruction, I basically increment that program counter and go to the next instruction and continue doing that. Okay? So basically, the sequential process looks like this. I start with the PC saying that, okay, this is the current instruction. Then I need to go and fetch that instructions from the memory. So this is the process that we usually call fetching. Since the CPU is a different location than the memory, I need to go and bring that. So this is the process of data movement between the memory and the processor. Then I actually execute that instruction. The process of execution is mainly updating some different states. Depending on the type of instructions that we're going to talk about, these states might be different. So I need to store those states. And then I repeat this process. I go to the next instruction and repeat this process over and over again. Okay? So this is basically what we are following in what we call a stored program order. The alternative to the von Neumann model is what we call a data only, or there are actually various different modes, but the main one is data flow processors. In a data flow processor, you don't have the notion of instructions. Basically, your accelerators work like that. So for example, let's say all you need to do is matrix multiplication. You don't need to bring instructions that, oh, this is add and this is multiply. You basically create the data flow in the hardware itself, so that you just feed the data and then it produces the results for you. Okay? But in majority of systems, since I need programmability, I need to be able to run different instructions and different programs, then I would need this kind of sequence of instructions one after another. Okay? So now that we understand this is the setup, let's see how we actually build an ISA. So if you remember last, you got a question? Yeah. The question is it not insecure that if you are able to modify instructions, And yes, that's actually the entire problem of memory vulnerability. So the whole buffer overflow and all the problems that came with it because of this very, very fact. But keep in mind that for functionality, we do need to modify instructions, right? So you need to be able to update things, change things, add things. If it's rigid, then you don't have programmability, right? You buy a laptop that you can never update you cannot install any new software on it, right? So it's not going to be possible. Any other questions? Okay. So what are the process in order to build an ISA? So remember I told you that we start with an algorithm and high-level language like a C and Python. We take that instruction, high-level language, and we translate it into what we call an assembly. The assembly is basically based on the ISA. Okay, so if I use RISC-V ISA, the assembly that I generate is going to be based on the ISA. Okay, then once I have my ISA, then I'll go with generating what we call a machine code. The machine code is basically based on the specific of the hardware. And from that, we need to somehow upload that into the hardware. We need to upload that into the memory of that hardware. And then we need to be able to run that in our hardware. So this is kind of like a very simplistic version of how do we run programs in our computers. Okay? So let's focus on this one first. And then we're going to talk a little bit about this one in this lecture as well. And next week, we're going to basically talk about these two other parts. Okay? So how do we actually create an assembly instructions? At the very high level, any instructions can be considered as two parts, commands and operands, okay? Since we are basically focusing on 32-bit RISC-V, the entire instruction is always 32-bit long. So this entire thing is 32-bit, and it's always 32-bit. So we don't have 64-bit version or 16-bit version, okay? So let's actually now focus on what sort of commands do we have and what sort of operands do we have. Let's focus on the operands first. So there's three types of operands you can see in any standard ISA. And again, from now on, I'm just going to focus on RISC-V. I'm not going to talk about OR and MIPS and so on, but they're fairly similar. We usually have what we call registers. We have what we call immediates, and we have memories. Registers are the easiest one to think about. Usually there's a small amount of storage within the CPU itself, which we call register file. This is a sequence of registers, usually 32 of them or 64 of them, that acts as like your variables. We really love these registers because they are very, very fast to access, but they also have memory, right? So they can store numbers, and they can really access it within one cycle because they're literally within the CPU itself. Okay, so I want to be able to majority of time using the registers. Okay, the reason that they're fast and they're small is that generally in designing memory in microelectronics, smaller is faster. If we want to increase the size, unfortunately, I have to use different technologies. And different technologies are slower. So for example, for a register file, we typically use what we call flip-flops. Flip-flops are very, very fast, but they're very, very expensive in terms of area. You need many, many transistors to just store 1 bit, okay? So if I want to, for example, have 1 gigabyte of memory, I cannot use 1 gigabyte flip-flop because it would be massive, it would be very power hungry. So then I need to go to another technology like an SRAM technology or DRAM technology. We're not going to talk about these technologies, but just know that they exist, okay? So register files is very small, but very fast, can be technically seen by the software, which means that I can basically say, I want to write it to X1 versus X2 or X3. I can basically pick the registers that I want. The reason that I have this asterisk here is that there is the difference between what we call an architectural and hardware registers, that there are some registers that are actually not seen by the programmer, but generally registers can be seen by the programmer. Typically, we have somewhere between 16 to 64 registers. We cannot really go beyond that because it's very, very expensive, okay? Register width is also another thing. So you can have multiple registers, but the size of the registers can be bigger or smaller. Typically, if we are going with 32-bit instruction set, it's easy to use the same size registers because that makes things easier to handle. So typically we go with the same size as our instruction. So if you are dealing with 32 bits instruction size ISA, our registers are also 32-bit wide. Okay, but generally, wider it is, I can do more things at the same time. But wider it is means that it also requires more power. So there's this trade-off that you need to understand. And then the trade-off again between like high-end processor and low-end processor is that high-end processor use more number of registers and wider registers. So for example, your laptop or server typically has 64-bit architectures, but if you go to your microcontroller or your mobile phones, these are usually 32-bit or sometimes even 16-bit, or at the very low end, it would be even 8-bit instructions. Okay. In RISC-V, the terminology that we use is that generally we have 32 registers. Each one is 32-bit. A 32-bit wide in RISC-V technology is called board. Okay, and if you have a 64-bit register, it's called double board. Okay, so if you see the word board, it means that it's 32-bit. If it's double board, it's 64-bit. As I said, we are focusing on RV32, but there exists the RV64 version. RV64 version is still 32 registers, but each one is 64-bit wide. Okay. In RISC-V, we use the terminology X to show the registers. The numbers start from 0 and goes all the way to X31. X0 is hardwired to 0. It's generally generating 0 because 0 is very useful in many cases. So if you write to X0, nothing happens. It always stays at 0. Okay. But other registers, they're stored in the register file. The register file is this data structure. Think about it as an array. So essentially, you can from the programmer's perspective, you can add access registers like this, or sometimes we show it like this. Okay, so X1, X2, X3. It means that I'm actually accessing the particular register from there. And the way that we can address this is that we put the index. So we put index 3, and I'm accessing register 3. Question? Yeah, the question is about the larger width means more data to transfer. Yeah, it means that I have a wider register so I can bring more data at the same time. Yes. Yes, so the question is that once things become cheaper and cheaper, can we actually scale the number of registers? And yes, in fact, yeah. The reason actually that you see this thing I'm showing you here, that registers can be seen by software, means that if I want to increase the number of registers, then I need to go back and change the software. And this is the part that I don't like. So I actually do this trick that I kind of do mapping. So I see one registers and I have an internal mapping that I assign it to various different registers. So that way I can increase the number of registers. Later, you're going to see that. This is actually going to be, we're going to spend quite some time on that. Questions? For now, just assume that there is literally 32 registers implemented in hardware, can be seen by software. Later, we're going to change that assumption. Okay? All right. All right. So the register file is this data structure. It's actually literally a hardware unit that stores these registers. It's very power hungry because the storing and writing and reading from registers is quite time consuming and power consuming as well. Okay. And then the registers that we are dealing with are integers. So all the numbers that we are dealing with in the base version are just integer numbers. There is a separate register file and separate set of registers for floating point operations. Okay, that usually shown by the word F. So when you see X is integer registers, when you see word F is floating point registers. We're not going to go through the floating point design operations and register file because we are mainly looking at like the simplest version. But for high-end processors, obviously, you definitely need floating point operations because that's the majority of operations we are dealing with. Usually, we separate the integers from the floating points. All right, so that's the story with registers. The second type of operands that we are seeing a lot is called immediates. Immediates are literally numbers. Okay, so it's actually instead of like dealing with reading and writing to the registers, sometimes I just need to increment something by 1 or 2 or 4 or 5. Instead of like storing 1 into the registers and kind of occupying one register, it's a good idea to actually embed that number into the instruction itself, okay? So in RISC-V terminology, we usually use this term I. When I, you see, added to an instruction means that this is an immediate operation, which means that one of the operands is an immediate. So in generally in RISC-V, what you will see is that we typically write it from left to right, and this one is called destination register. This is the destination. This is the left side of the equation, and these are the operands, so x1 and 5. So what this instruction does is basically says that x2 is equal to x1 plus 5. As you can see, 5 is an operand here, but it's a number. It's not the register itself. So we actually embed this into the instruction itself, okay? I'm going to show you how do we do that, but generally know that this is separate from the register itself, okay? As I said, these are constant numbers, and then remember that the entire instruction is 32 bits. So immediate is basically limited by how long an instruction is. And as you will see later, different instructions might need different things. So some of them needs different sources, different destination, opcode, and so on and so forth. So so immediates may not be 32 bits, okay? So for example, let's say in the instruction, I only have 4 bits to encode an immediate. So it's a 4-bit number. But as you can see here, I need to add a 4-bit number to a 32-bit number, right? Because these are the operands of the same instructions. So how do we fix that issue? Anyone? Yeah. Yeah, you extend it. You sign extend it. Generally, you extend it. So the dumbest thing that you can do is, simplest thing that you can do is that if it's 4-bit, you just add zeros to it and it becomes 32-bit. And then these 32-bit numbers, you can add them. But as I said, since these are integers, so they are signed, you have to be careful about the way that you extend them. So you sign extend them to make it 32-bit, okay? For those of you who don't remember what it was, sign extension, the TA are going to go over sign extension. You probably have seen it in the past. So there's this thing called 2's complement that you basically kind of padding it and making sure that the least significant bit or most significant bits are properly sign extended. Again, for those of you who don't remember it, the book actually has a nice kind of a subsection about sign extension. The TA will also go over it. So please make sure that you understand sign extensions because you're going to need it later in the course. Okay? Any questions here? Okay. All right, so that's that with immediates. The third thing is memory. Memory, of course, is anything beyond the register file. As I said, generally you want to store everything in the register file. The reality though is that your register file is small, so you cannot store everything. So there's like occasionally you need to go and grab things from the memory. From the ISA perspective, we don't understand the difference between different type of memory. We don't understand there is like a cache or main memory or hard drive. We just call this a memory. And you can think about this as this giant array that you can basically index it with the address, okay? So you put an address, somehow magically the hardware gonna go and grab the data that you want. Later on in the course, you're gonna actually abstract away the memory and show you there is a hierarchy within the memory that is very, very important. But for now, just basically everything is in the memory. It's an array outside the CPU. The difference between memory and register file is that accessing memory usually takes significant more amount of time. For now, for simplicity, we can assume that everything is instantly accessible. But later on, you're going to see that the reason that things are faster versus slower is that it takes more time to store things, to access things, okay? So usually the two main operations that we have for the memory is called load and store, okay? So loading is basically when we are reading something from the memory. So think about memory and the processor as kind of two blocks. So this is my CPU and this is my memory, okay? And I usually put an address and then I get my data, okay? So the process of loading is basically you load an instruction. So we typically like load board which means that I read 32 bit of data, which means that I put the address. For now, I'm not gonna use the actual syntax, but I put the address, I get the data. Okay, this is the process of loading. Storing is the opposite. So storing is I put the address and data. Okay, so this is a store word. I put the address and data, and memory just stores it. So I just say, okay, here's the address, here's your data, go and store it. I just move on. Okay, so the load process is kind of like usually much slower than the store process. Why? Because I need for the memory to give me the data back, and then in that process I need to wait. Whereas in the store, I can just basically dump it to the memory and move on. Okay. There is different types of storing and loading in RISC-V that we're going to actually talk about. Before that, generally there are different format of addressing in ISA, specifically for RISC-V. So you typically we go with what we call a base plus offset addressing. Okay. The reason that we want to have this base plus offset addressing is that we don't want to provide the one number and then change that number, but we sometimes we want to, for example, say that okay, we don't know exactly where it is, but all I know is that it's actually like 4 blocks away from the space. So for example, if you think about an array, right? So for example, I have an array A. I don't know the exact address of A, but what I do know is that, for example, I want index 4 of that. Okay. So how does this translate into an actual address? Is that this A itself is actually has a base. Okay. So this A is actually pointing to the beginning of this array A is pointing to a specific part of the memory, and whatever that memory is, added by 4 will give me the 4th index of that array. Okay. So usually the addressing in any ISA is based on this base plus offset format that you're going to see. Okay. The third thing that is very important for memory is byte addressability versus word data that you want to access. Remember, I told you that registers in RISC-V are 32 bits. Okay. So it's natural that if I want to read something from the memory, I read things in chunks of 32, right? Because that's the fastest. I can occupy just one register, write things in 32-bit chunks, and read things from the 32-bit chunks, okay? But it's very important in legacy systems to maintain what we call byte addressability. That is, I need to be able to access the memory at byte level. I don't want to be access the memory at 4-byte level. I want to be able to access memory at the byte level. Okay, that creates a little bit of complication because now I need to kind of transfer and translate 32 bits and then bring, divide it into chunks, right? So the 32-bit is basically 4 bytes, but now I need to be able to be byte addressable. So how do we actually store these numbers into the memory? So memory is basically each row of memory only stores 1 byte. Because as I said, I want to have unique addresses for each byte. And that's why my memory is always 8 bits total. Okay? So if I want to read something 32 bits, basically what happens is that the process of loading is in fact 4 1-byte loads. So if I want to load one word, which is 32-bit, I basically issue 4 smaller loads inside the memory. From the CPU's perspective, this is still one load, but the way it's handled in hardware is that this is basically combining these 4 bytes together and give you that 32-bit value. Okay? So if I have this, then the question becomes, how do I store these 4 bytes? Okay? So the difference between them is what we call big Indian versus little Indian. So do I store it like this? So this would be address 0, this would be address 1, this would be address 2, this would be address 3, and this is your most significant bit, and this is your least significant bit. This is one option. So lower addresses store lower value. The other option is the opposite of this, that higher values is stored in lower bits. So I stored this in address 0, I stored this in address 1, I stored this in address 2, I stored this in address 3. The importance of this is doesn't really matter in terms of performance. So they both result in the exact same thing. The only thing is that they need to be on the same page. That is, the memory and the CPU should understand that they're working on a little endian format or a bigger endian format. Okay? Typically, we go little endian, but there are some systems that like big endian. But generally, it's not a specific reason to go one way or another. The blue format is usually more intuitive because you would expect that lower bits are in lower addresses and higher bits in the higher addresses. But generally, as I said, there are systems that are actually doing the opposite. So just keep in mind that this exists. Okay. We usually go with the blue format. Okay, but if we say that this is little endian or big endian, you would see that. So for example, this is the example of like how do I store this. The second thing is the alignment issue. The alignment issue is when I want to read 4 bytes, and these are actually stored not in the same row, but rather in 2 different rows. So for example, let's say I stored one register like this, and I have another register like this, and now I want to read at another 32 bits. That this 32 bits kind of stores from here, here, here. Okay, so this will require us to basically issue, for example, 2 loads or 2 moves, because essentially I need 1 byte of 132 and then another 3 bytes or 2 bytes. Typically, most hardware systems doesn't allow you to do this kind of things. They usually block you from misaligned reads or writes. They need you to actually be able to do it in two separate issues. So, for example, if I want something like this into the memory, I need to issue one store here and another store here, and I need to somehow mask these data from being written to the memory. Okay. We're going to talk about kind of data management, but just keep in mind that if these are not aligned perfectly, starting from 0 to 3 and then 4 to 7, so the power of 2, then this is a misaligned load or store, and either I need to basically issue multiple of this, or I need to add additional hardware to be able to handle this. RISC-V doesn't allow you to do this kind of thing, so you actually need to issue 2 separate loads. Intel processors, for example, usually allow for misalignment. Yeah. Not being aligned properly? Yeah. So for example, let's say I read this bytes, right? Initially, and then I get this 4 bytes, okay? And now the next thing I want to store is that I don't want to store the entire thing, but I want to store it starting from byte 3. Okay? So I want to store the 32-bit value and start from byte back to the middle. Okay? So how do I do that? Either I need to be able to somehow say that byte 3 of this 32 and then the first 3 bytes of the next 32 is what I want to write. And so I need to somehow kind of like mix and match this. Or I say that I don't understand this misalignment. If you want to write it that way, issue 2 stores. Issue store number 1 and I'll only store your byte 3. Issue another store and I will store 4, 5, and 6. Okay? But you also need to somehow tell the memory that from the first store only pick 3, from the second store only pick 4, 5, and 6. So there's a little bit of kind of like data mapping that you need to figure out. Yes. Yeah, so the question is about like the mapping here. Yes, so the gray ones are the ones that we want to actually write. Yes, so I want to write 3, 4, 5, and 6. Yes, so it's the programmer's job, right? So you, as a programmer, you need to figure this. Any other questions? Okay. All right. So in RISC-V, the terminology that we use for loading and storing is the word L and S. So we have S, but then since we have bytes, 1 byte, or 2 bytes, or 4 bytes variants, we have different wording for it. So if I want to store the entire 32 bits, I use the word W, word. So I store load word. So it means that I store the entire 32 bits. If I just want to store 1 byte, I do LB. So I store only 1 byte. If I want to store half of the word, which is 16 bits or 2 bytes, I do LH. Okay, so load half word. Okay, and then I can also store things in an unsigned way. So remember, since I writing a 32-bit value to an 8-bit value. For example, if I want to store 1 byte, uh, and then the value that I'm storing is the value I'm loading is sorry, it's the other way around. I'm loading only 8 bits, but I want to load it into a 32-bit register, right? So, for example, let's say I have a 32-bit register. This is the first byte, second byte, third byte, and I only wants to basically fill the first byte. Okay. So now the question is, what do I do with the other 3 bytes? Do I leave them at 0? Do I sign extend the first byte and then store it in the other 3 bytes? So that's where you can actually tell which one you want to use. If I don't specify what I want to do, like do load bytes, it automatically sign extend. So whatever the sign of the first byte is, it will extend it to the rest of the register. But if I don't want sign extension, I use the word U. So it's saying that load bytes unsigned. So I basically just load the first byte, leave the rest whatever it was before. Okay, it might be zeros or anything else. Same story for half, right? So again, for half, I'm loading these 2 first bytes. So the other 2 bytes needs to be either sign extend or left alone. So basically, this is the difference between load half and load full. On the store, though, store is different. On store, you write it to the memory. So again, you can do store word, which means that I provide a 32-bit value to you. Go and write it in 0, 1, 2, 3, and 0, 1, 2, and 3. And then again, whether you want to store the lower bytes in the lower address or higher address depends on the Indianness. If you go little Indian versus a big Indian. Store bytes means that I provide a byte to you. Go and write it to that one particular byte. Okay. And basically the way this works is that if you provide a 32-bit register, it basically just takes the first byte and writes it. It ignores the rest of the register. And lastly, if you have a store half byte, it means that I just takes the first 2 bytes and store it there. And again, here I don't need to care about the sign. Essentially, as a programmer, you are the one who needs to be worried about the sign. Yes. Left to right. So the question is, are we talking about left to right or right to left? That depends on the Indianness, right? So if I store the lower bytes, right? So if I want to store 1 byte here, I usually store the 0 to the bit 0 to bit 7 to that address. Okay, it's the first byte. Yes. Yes. Little. Mm-hmm. You got a question there? Yeah. Yes. Yeah, so the question is the difference between load and store. So in RISC-V, you don't have the move operation. Move can be built based on load and store. So I'm going to talk about it later. But the difference between load and store is the operation itself. Load means that you're reading from the memory. Store means that we are writing to the memory. That's the difference. And then word versus byte is just how much we are reading or how much we are writing. So, yeah. Okay, so these are your three operands. So we can, yes. Which one? This one? Oh, he asked question? Yes. Uh-huh. No, this is not an actual. I'm not showing you. Yeah, for now, don't worry about this. Yes. Yeah. Uh-huh. So the question is that when we are storing, we need to provide 4 addresses. We actually don't do that